Thanks for watching my video. Today let's discuss our fundamental theorem of calculus or integral calculus 2, which states that if f is continuous, if a function f of x is continuous at every point of this between a and b, and f is capital F is any antiderivative. Antiderivative means the integral of f on ab, then integral from a to b f of x dx is f of upper limit then is b minus f of lower limit then is a. So we are going to prove this today. Now let us define, in order to prove this, let us define a function. Let us define a function g on closed interval ab. Okay, this function g is between a and b. Now by g of x is integral from a to x f of t dt, such that x is between a and b. Now from fundamental theorem of calculus 1 that we have proved in the previous one, g has a derivative at every point on closed interval AB. This we have discussed in the previous video. You can check it out. So if I take the derivative with respect to x, this will give d by dx of integral from a to x f of t dt, and this you get f of x, where x is between a and b. Now given f is antiderivative of f on closed interval ab, we are given that our function capital F is antiderivative, which means df by dx will be f of x. If you take the integral, then you get different antiderivative, where this x is between a and b. Now thus on closed interval ab, both f and g has the same derivative. Now we know that function with identical derivative differ only by a constant that I have proved in properties of indefinite integral. So what can we get from here? That means this f of x and g of x is just differ only by constant, function constant. Well, c is a constant constant known as constant of integration. Then now we are going to apply this right hand side. So f of b is equal to g of b plus some constant, and f of a is g of a plus some constant. Now we are going to subtract this one here. Okay. Now this we are going to subtract f of b minus f of a, which is f of b is g of b, and g of b plus c minus g of a plus c. Now if you open the bracket, g of b minus g of a, which means g of b is nothing but our function g of x. If you put here g of b, that means integral from a to b f of t dt minus this one integral from a to a f of t dt. But integral from a to a f of t dt is 0. Therefore we can conclude that integral from a to b f of t dt is equal to f of b minus f of a. Or in other words, I can write integral from a to b f of x dx is f of b minus f of a. So this proves our fundamental theorem.